In today's video, we're going to be taking a look at flight physics. So let me try to explain the basics of flight physics. So if we imagine that we have 5 parts here, and this is the side view of these 5 parts. And let's also imagine that surrounding these 5 parts is static air. And if I now apply a force onto these 5 parts, pushing them towards the left side, they're going to start moving towards the left, while the air stays static, and the air is going to start to collide into the parts. You can imagine this like when you're driving in a car and you stick your hand outside of the window and the air collides with your hand. So if we try to visualize how air will collide with each one of these parts, we can imagine that air is going to collide into the front of this part and then bounce off this small surface and get redirected around the part. Something like this. And because the surface area of the front of this part is kind of small, it's only going to produce a small amount of drag, pushing the part backwards. But if we visualize air colliding with this part at the bottom, because it has a larger surface area, it's going to have more particles collide into the front of the part. And because more particles are colliding with the part, it's going to produce more drag. So this drag vector is going to be larger than the drag vector from this part that's hitting with a small surface area. And if we also visualize air colliding with this tilted part, we can visualize the air coming along, colliding with this tilted surface, and it will be reflected downwards like so. And this is going to produce a counter force pushing the part upwards. And if we have an even greater tilt, air is going to be reflected even more like so. And this is going to produce an even stronger force pushing backwards like so. And finally, if we look at the top part, we'll see it's tilted in the opposite direction. So air is going to be coming along and it will be reflected upwards instead of downwards. And instead of causing a force that goes upwards, it's going to cause a force that goes downwards, So how would we go about calculating these red drag vectors without having to simulate each individual air particle? And the answer is we would get the direction that the air particle collided with the part, then we would get the up vector of the part, and then we would use the dot product of these two vectors, and then we would multiply it by the surface area of the top of the part. And then we'll do the same thing again, but this time instead of using the up vector, we're going to use the look vector. So we're going to get the direction that the air particle collided with the part, then we're going to use the dot product with the look vector, and then we're going to multiply this dot product with the surface area of the front of the part. And finally, we're going to add both the result from the up vector and the look vector together to get the final drag vector. Let's now do the math to calculate the drag for these two parts. Now let's imagine that the air is always colliding with the part from the left side, and let's imagine that the part has an area of 1 at the front and an area of 5 at the top. And let's say that the look vector of this part is coming out the front over here, like in this direction, and the up vector is pointing at the top on this direction. And for this part at the bottom, the look vector is pointing at the front over here like this, and the up vector is pointing at the top like this. So let's now get the dot product of the air direction and the look direction. So here we can see two directions, and let's assume that the green direction is the look direction, so we're looking towards the left. And let's assume that the red direction is the air direction, which is looking towards the right. And we can see that we get a value of -1. And now we're going to multiply this -1 with the surface area, which is 1. So -1 multiplied by 1 is equal to -1. And then we're going to multiply this -1 value with the look vector, which is essentially going to flip the vector to point the opposite direction. So this is going to result in a vector looking in this direction with a magnitude of the value of 1. And let's now do the up vector. So just like before, the air is still pointing to the right, so this red vector is going to stay the same, but let's move this green vector to be the same as the up vector, which is pointing upwards like this. And we can see that this gives us a result of 0. So what we need to do now is multiply the surface area of the top with 0, and then multiply that value with the up vector. So to do this, we're going to say 0 multiplied by 5, because the top surface is a surface area of 5, is equal to 0. And now we're going to multiply the up vector with 0, which is essentially going to cancel the up vector and return a vector with the values of 0, 0, 0. So it's not going to point in any direction, and it's going to have a magnitude of 0. And so now all we need to do is add these two vectors together. So a vector with a magnitude of 1 pointing to the right plus a vector with 0, 0, 0 will equal to a vector pointing to the right with a magnitude of 1. So let's now do the same again, but this time for the part at the bottom. So the look vector is pointing up in this direction. So let's move this green direction to be roughly about the same. And let's get the value from here. So we can see it's -0.69. And we want to multiply this value with the surface area, which is 1. So -0.69 multiplied by 1 is equal to -0.69. So let's write that down. -0.69 multiplied by 1 is equal to -0.69. And now let's multiply -0.69 with the look vector. So that's going to flip the vector around because it's a negative number, but it's not going to have a magnitude of 1, it's going to have a magnitude of 0.69. So it's going to produce a vector pointing in this direction with a magnitude of 0.69. 6, 9. So let's now do the same, but with the up vector. So I'm going to move this green direction to point in roughly the same direction as the up vector. And we can see it has a value of 0.69. So we're going to multiply 0.69 with the surface area, which is 5. So 0.69 multiplied by 5 is equal to 3.45. So let's now write that down. So value dot product was 0.69 multiplied by the surface area, which is 5, is equal to 3.45. And so now let's multiply 3.45 with the up vector. So that's going to produce a vector looking in the same direction, but with a magnitude of 3.45. Let's now use this tool to visualize what it's like to add two vectors together. So here we can see a vector over here, and we can see another vector over here. And this blue vector, darker blue vector in the center, is what it would look like if we added these two vectors together. So if I put this down here, we can see that the blue vector is now equal to 0 because both vectors cancel each other out. If I move this over here, it goes like this, and if I move it around like here, you can see how adding two vectors together produces a different vector. So let's assume that this left vector is this one over here, and this right vector is this one over here, and let's add them together to see what kind of vector it produces. So let's make a small vector of 0.69 that points down to the right. So let's move this down. But the smallest I can go is 1.4. So let's just use 1.4 for now. So it's not going to give us an exact result, but it should give us a ballpark figure of what it's going to be. And let's move this to a distance of around 5. And now we can see that if we add these two vectors together, it's going to produce a vector that points in this direction like this. So that means by adding these two vectors together, we should get a vector that's roughly pointing in this direction. And the magnitude should be roughly around 4. And finally, all we need to do is multiply these vectors with the velocity squared and the air density of the surrounding air. So let's just imagine that the air density is equal to 1 and the part is moving at 1 stud per second. So we just multiply these by 1 and it would result in a force that would push the part in this direction by 1. And this part will have a force that pushes the part in this direction with the value of 4. So what I've done now is created a base plate project and published this place to Roblox. And the first thing we're going to want to do is adjust Roblox's default gravity settings. So if we go into game settings and click on world, we'll see that currently gravity is set to 54.936 meters per second squared. Now this is very high compared to Earth. So what we can do is simply press realistic, and this is going to adjust it to 9.8 meters per second squared. And then I'm going to press save. And what I'm going to do now, inside of Workspace, I'm going to create a model. And inside of this model, I'm going to create a vehicle seat. And what I want to do now is detect when a player sits on this seat, and I want to give them network ownership of this seat's assembly. So to do this, inside of Server Script Service, I'm going to create a new script, and I'm going to name this script Network Owner, and I'm going to delete this print over here. And now what I want to do is connect to each player's humanoid's seated event. So to do this, I'm going to say game.players.playerAdded, and I'm going to connect a function. So let's create our function. So I'm going to say local function player added, and this function is going to tell us which player was added. And let's pass this function into the event so that this function is called. And inside of the player added function, I want to detect when a character is added. So let's first create our character added function. And this is going to tell us which character was added. And in here, I'm going to connect to this function. And finally, let's connect to the seated event. So let's first create our seated function. And let's now connect this function. The first thing I'm going to do is check this active variable because I only want to give them network ownership when they sit down and not when they stand up. So the first thing I'm going to do is say if active equals false, then return, and this is going to exit the function and do nothing. The next thing I want to do is check which seat I sat on, because we may have hundreds of seats in our game and I only want this function to work for planes. So what I'm going to do is I'm going to change the name of the seat to plane, and then I'm going to check to make sure that this seat's name is equal to plane, and if it's not, I'm going to exit out of this function and do nothing. The next thing I want to do is to find out which player sat on the seat, and we can do this by using the seat's occupancy property. So what I'm going to say is local player equals game.players get player from character, and I'm going to use the seat occupancy.parent. And just to be certain, I'm going to check the player variable and make sure it's not equal to nil. So I'm going to say if player is equal to nil, then return. And now that we know who the player is, let's set this player as the network owner. So to do that, I'm going to say seat set network owner player. And just for testing, I'm going to print out that we set the player. So I'm going to say print set network owner, and I'm going to print the player's display name. So let's now test the game. So every time I sit down on the seat, it should say set network owner with my display name. And if I get off and go back on, it should say the same thing again. Okay, so now that our network owner script has been finished, and we're now giving network ownership to the client when they sit on the seat, let's create a local script inside of starter character scripts. And I'm going to name the script plane. And just like the network owner script, I want to detect when the local character sits or gets off of the plane seat. So the first thing I'm going to do is get the character by saying character equals script.parent, and then I'm going to wait for the humanoid. And once we have the humanoid, I'm going to connect to the seated event. So let's first create our function, local function seated, and then let's connect this function to the seated event. Humanoid.seated connect, and we're going to pass in the seated function. So what I want to do now is create 3 functions. The first function I'm going to create is called start, and this function is going to be called when the player sits on a plane. The next function I want to make is called stop, and this function is going to be called when a player gets off the plane seat. And the final function that I want to create is called loop, and this function is going to loop every heartbeat while the player is sitting on the plane seat. Now, in order to connect to the heartbeat event for the loop function, we're going to need the run service. So let's first get the run service. And let's also store the connection so we can disconnect from it when we get off the seat. So let's create a variable called local connection equals nil. Another thing I want to store in a variable is the seat that we sat on. So at the top over here, I'm going to say local seat equals nil. And now inside of the seated event, I'm going to check whether or not we got on or off a seat by saying if active equals false. This means that we got off the seat. But if we got on a seat, I want to make sure that the seat's name is plane. So I'm going to say else if seat name equals plane, then. So the first thing I want to do when we sit on the plane seat is set the seat to the current seat. So to do this, I'm going to say seat equals current seat, and then I'm going to start the start function. So I'm going to just call the start function, and then I'm going to connect to the run service's heartbeat event. So we can do this by saying connection equals run service, post simulation, connect, and we're going to pass in the loop function. And when we get off the seat, the first thing I want to check is make sure that we have this connection, because if we sat on a seat that is not called plane, this part is still going to get called and we don't have a connection if it's not a plane, so we need to make sure we have a connection. So to do this, I'm going to say if connection is equal to nil, then return and do nothing. But if we do have a connection, I'm going to first disconnect that connection. So I'm going to say connection, disconnect, and that's going to stop this loop from continuing to run. Then I'm going to set the connection to a value of nil. And then I'm going to call the stop function. So I'm going to say stop. And finally, this is not mandatory, but if we want to, we can set seat back to nil. So I'm going to say seat equals nil. And in order to test to see if our code is working correctly, I'm just going to simply print start. And I'm going to print stop. And I'm going to print loop. So let's now sit on the seat for a very short period of time. We can see that first the server gives us network ownership, then we call the start function, then the loop function called many times every heartbeat, and then once we got off, the stop function called. Let's try it again. You can see it happened a second time. Okay, let's now add a second part to our plane model. So inside of this model, I'm going to create a part, and then I'm going to go into the model tab, and I'm going to select the part, and I'm going to weld this part to the seat. So over here where it says create, I'm going to select a weld. So let's find weld, I'm going to click, and then I'm going to click on the seat. And this is going to create a weld constraint. So what I want to do now is loop every part inside of the model, and I want to connect a beam to each part. And we're going to use this beam to indicate the force that's applied to this part. So I'm going to go back into the plane script, and the first thing I'm going to do is delete the prints. And then I'm going to use this seat variable to find the model. So to do that, I'm going to say local model equals seat, find first ancestor of class model. And then I'm going to loop each descendant of the model. Now the reason I'm going to use descendant instead of child is because in the future we're going to add hinges, and we're also going to use this loop to find the hinges. So to do this, I'm going to say for index descendant in model get descendants. And in this part, I'm going to check the descendant to make sure it's a base part. So I'm going to say if descendant is a base part equals true, then. And now for each descendant, which is a base part, I'm going to create two attachments. So let's first create two attachments and parent them to the descendant. And then let's create the beam, and let's set face camera to true, set segments to 1, set the width to 0.2, let's set it to a red color, and let's set the attachments of the beam to attachment 0 and 1, and let's finally set the parent of the beam into the descendant. If we now test again and open the workspace and look within the model, we can see the two parts of the model. And if we sit down, we can see that the two attachments and the beam get created for both of the parts. But because we're creating these parts within a local script, if we go to the server side by clicking on this button over here and check the model on the server side, we should see that these beams and attachments do not replicate to the server. Okay, so what I want to do now is destroy these attachments and beams when we get off the seat. So to do this, I'm going to first create a table. So at the top here, I'm going to say local parts equal table, and then I'm going to insert the attachments and beam into this parts table when we loop the descendants. So over here, I'm going to say table.insert into the parts table, and I'm going to insert attachment 0 like this, and then I'm going to insert attachment 1 like this, and then I'm going to insert the beam. So now when we get off of the part and the stop function is called, let's loop the parts table and destroy these 3 instances that we saved into the table. So to do this, I'm going to say for index data in parts do, and I'm going to destroy the 3 instances. And once we've destroyed these instances, now we must clear the parts table to make it an empty table. So to do this, a simple way would be to say parts equals empty table, and this will replace the previous table with a new table. But another option that we have is to say table.clear and parts. And what this is going to do is going to empty the table, but without deallocating any memory from the table. Let's now loop all the parts inside of this loop, and let's set the position of attachment 1. So to do this, I'm going to do the loop just like I did here, over here, and then I'm going to say data.attachment1. So we're going to use attachment 1, not 0. And I'm going to say dot position equals vector3.new. And just for now, I'm going to set it to a position of 10 on the y-axis. And if we now play the game and take a look inside of the model once again, and if we sit on the seat, we can see the beams are created with the 2 attachments on both the parts. And when we get off the seat, we can see they're destroyed and the beams disappear. We can sit back for the beams to come back, come off, and the beams go away. Okay, let's now add a motor to our model so we can push the model forward. So inside of the model, I'm going to duplicate the part, and then I'm going to move this part to the front, and I'm going to rename this part to motor. And then I'm going to change the color of this motor so it's more distinct. I'm going to set it to a dark color, and I'm going to set the size of this motor to something like this, and place it at the front. And now I'm going to go back into my plain script, and the first thing I want is a thrust variable. So over here, I'm going to create a new variable called thrust and equals to 0. Now, inside of the loop, I'm going to detect when the Q or E keys are pressed in order to adjust the thrust. So the first thing we're going to need is the user input service. So let's first get the user input service. And then inside of the loop, I'm going to detect when the E or Q key is pressed and adjust the thrust. So to do this, I'm going to say if user input service is keyed down, key code E equals true. I'm going to add 2000 to the thrust, but I'm going to multiply it by delta time, which is going to mean that we're going to add 2000 every second to the thrust. And if we press the Q key, I'm going to subtract 2000 every second from the thrust variable. And what I want to do now is add a vector force for every part inside of the model. And we're going to use that vector force for the drag force plus for the motor forces. So over here, after we've created the beam, I'm going to say vector force equals instance new vector force, and I'm going to attach the attachment to attachment 0. And then I'm going to parent the vector force to the descendant. And finally, I want to add this vector force to the parts table. So over here, I'm going to say vector force equals vector force. And let's also make sure to destroy the vector force when we get off of the plane. So over here, I'm going to say data vector force destroy. And then over here, when we loop each part, I'm going to check the part to see if it's a motor. Now, currently we don't have access to this descendant. So what we need to do is save this descendant into the parts table. So over here, I'm going to say part equals descendant. So now we can access this descendant part over here in the loop. And I'm first going to check the part's name. So I'm going to say if data.part.name equals motor, then, and if it is equal to motor, we're going to use the thrust variable to set the vector false in this part. So I'm going to say data.vectorFalse.false equals, we're going to create a new vector3, and we're going to use the thrust variable, but we're going to use a negative value because the z-axis is flipped. And then I'm going to say else, and if the name is not equal to motor, I'm going to simply set the vector false's false to 0. So to do this, I'm going to say data.vectorFalse.false equals vector3.0. And then instead of using this vector3 to position the attachment 1, I'm now going to use the vector false's false instead. But because this false is going to be quite large, I'm going to divide it by 200 so that the beams don't get too long. And if I now test again and sit on the seat, we can see that we currently can't see no beams because they're all set to 0. And if I hold the E key, we can see that the motor beam increases, and if I hold the Q key, we can see it decreases. And now I can push and pull the model forward. Let's now create hinges to create control surfaces in order to control our plane's yaw, pitch and roll. So to do this, I'm going to duplicate this part, and I'm going to move this part to the end, like so, and I'm going to scale this part down, and I'm also going to scale it down on this side. And then I'm going to delete the weld so it's no longer welded to the seat. And what I want to do now is create an attachment for this part, and then use a hinge to connect the two attachments together. So let's first create an attachment for this part. And I'm going to move this attachment so it's right at the crease where it touches this part. And we should see now this attachment is perfectly in line with the crease. And then I'm going to create an attachment for this large part. And I want this attachment to be in line with this attachment, and the easy way to do this is to copy the weld position and paste the weld position into this attachment. And now both attachments should be on top of one another. And let's now create the hinge and use these two attachments. So inside of this part, I'm going to create a hinge. And then I'm going to set attachment 0 to the attachment in the part, and attachment 1 to the attachment in the big part. And then I'm going to set the actuator type to servo. And then I'm going to set the angle speed. You can have any speed you like, but I'm going to set it to 10. And for the max torque, I'm going to set it to a large number of 10,000. And let's now make a duplicate of this control surface. So to do this, I'm going to select the part, and I'm going to select the attachment inside of the big part. And then I'm going to press Ctrl D to make a duplicate. And then I'm going to move the duplicate to the right, and it should move all the attachments correctly, so we don't have to change anything. And if we check the hinge, we can see that this has a hinge on this side. We click on this hinge, we can see that this has the hinge on this side. And what I want to do now is I want to control these hinges using the seats, steer float and throttle float. So if I select both of these hinges, and if I click on the add attribute, we should see this window pop up, and I'm going to set this to a number, and I'm going to set the name to throttle float so it matches the property inside of this seat. Then I'm going to press save, and I'm going to set this value to -20. And this is going to determine how much of an angle these hinges will rotate when we use throttle float. So let's now go back to the plane script, and let's now detect the hinges inside of the descendants loop. So at the very top, next to parts, I'm going to create a brand new table. And I'm going to say local hinges equals an empty table. And then over here, where we check to see if it's a base part, I'm also going to say else if descendant.className equals hinge constraint. This is going to check if the descendant is a hinge constraint. And if the descendant is a hinge constraint, unlike over here where we create a table with multiple properties, we're just going to add the descendant into the hinges table. So to do this, I'm going to say table.insert hinges, and we're just going to simply insert the descendant. And over here, when we clear the parts table, we're also going to do the same for the hinges table. So we're going to say table clear hinges. And now let's go down to our loop. And in here, we're going to loop all the hinges, and we're going to set the hinges target angle based on the seats, throttle float or steer float. So to do this, I'm going to come over here and I'm going to say for index hinge in hinges. So we're going to loop every hinge, and then I'm going to say hinge.target angle equals 0. So we're going to reset the target angle to 0 by default. And then I'm going to say for index value in hinge get attributes. So this is going to return a dictionary of all the attributes in the hinge. And we can see that the attribute has a throttle float. And then what I'm going to do is say hinge.target angle plus equals. So we're going to add to the 0 that we had from here. And we're going to use the seat with the index. And if we remember, the index is throttle float. And we're going to multiply it by the value of -20. And if we now test the game and sit on the seat, we can see if I press the W key, the hinges rotate by 20 degrees. And if I press the S key, they rotate by 20 degrees in the opposite direction. And if I press A and D, they currently do nothing. So let's now make these hinges also work for the A and D keys. So I'm going to select the hinge, then I'm going to press add attribute, set it to number, and I'm going to call this steer float. Press save, and I'm going to set the left hinge to be -20, and then I'm going to select the right hinge, and I'm going to also add an attribute to this one, number, steer float, and instead of being -20, I'm going to set this to +20. And if we now test the game and sit on the seat, we can see if I press the A key, they rotate in opposite directions by 20 degrees. And if I press the D key, they rotate the other way. And I can press the W and A at the same time to add the two rotations together. And I can press S and D together to have rotations together, like so. So now that we've finished the motor and hinges, let's now move on to flight physics. So if you remember from before, we had a vector which represents the direction that the particles are colliding into the part. So to get this vector, all we need to do is use the negative of the velocity of the part. So at the top of this loop, I'm going to say local velocity equals negative assembly linear velocity. And this is going to be the velocity that the air particles are colliding into the part at. The next thing we're going to need is the surface area of the part's sides. So here we can see we used the surface area of 1 and 5 in our demo, but because we're going to make a 3D game, not a 2D game, we're going to need the front, top, and right side of the surface area. So to do this, inside of the parts table, when we add all these instances into the table, let's also calculate the surface area and add it into this table as well, so that we can access it from inside of the loop. So to do this, I'm going to say area X, and we're going to multiply the sizes of the Y and Z axes to calculate the X surface area, and to calculate the Y surface area, we're going to multiply X and Z, and to calculate the Z surface area, we're going to multiply X and Y. And let's now go down to the loop. And inside of this loop, the first thing I'm going to do is check this velocity to make sure that the plane is moving. So to do this, I'm going to say if velocity.magnitude is greater than 0, then, and in here we're going to calculate the drag force. So let's now do the up vector first. So if you remember from before, we first get the dot product between the air's direction and the up direction. So to do this, all we're going to do is say local.up equals, and we're going to use the up vector dot, and we're going to use the velocity of the air, but we're going to unit this velocity so it has a magnitude of 1, and this is going to give us the dot product, and we're going to store it in this variable over here. So now that we've calculated the dot product, the next step is to multiply the dot product with the surface area and then multiply the up vector with that final value. So to do this, over here, I'm going to say data.vectorForce plus equals y-axis multiplied by dot up multiplied by the surface area. So here we need to make sure we use plus because we want to add onto the force that we set up here. We don't want to replace it. And then you may also be wondering, why are we using the y-axis instead of the up vector? Remember that this vector force is in object space, not world space. So this y-axis will be in object space. And then we're multiplying it by the dot product that we calculated here. And then we're multiplying it by the surface area, which we calculated up here. And we also must multiply this force by the magnitude squared of the velocity of the particles that collide with the plane. So to do this, I'm going to say multiplied by velocity dot magnitude to the power of 2. And finally, we need to set the air density of the particles that are colliding with the part. Now, for now, I'm just going to have a fixed value, but later on in the video, I'm going to show you how to dynamically adjust the air density based on the height of the plane. So for now, at the very top, I'm going to create a new variable called air density, and I'm going to set it to 0.01. Now, be careful when setting the air density to a high value because it can crash Studio. And I'm now going to take this air density and come down to where we set the force and also multiply this force with air density. So now that we've done the up vector, even though we have not done the look or right vector, the up vector is normally just enough to get the plane off the ground. So let's now test with just the up vector. And in order to test, I've created a wedge to use as a ramp to help the plane get off the ground. So let's jump in the plane and hold the E key to increase our thrust. And once we ramp off the edge of this part, we should be flying. And I can use the W key to tilt forward, and I can use the S key to tilt back. And I can reduce my thrust a little bit, and I can press the A key to rotate left, and I can press the D key to rotate right, but we can see that this plane is very unstable, and that's because the design of the plane is not very good, and also the other surfaces have no drag, so we currently only have drag on the top and bottom surface of the parts. So let's now do the surfaces for the other axes. So I'm going to copy and paste the up vector one, and I'm going to change this to right. And then we're going to use the right vector. And then I'm going to use this dot product to calculate the force. And I'm also going to use vector3 dot x axis. And also here for the area, we're going to use the x-axis. And let's now do the same for the look vector. So let's copy and paste this down here. I'm going to rename this to dot look. And I'm going to change this to look vector. And then I'm going to change the axes to z. And then we're going to use the look dot product over here instead of the right. And instead of using the X area, we're going to use the Z area. And now we should be calculating the force for all three axes. And one last thing we need to do is, just like how we reversed thrust, because the Z axis is reversed, we must also reverse the Z axis over here so it's correct. So this needs to be negative equals to this force. And if we now test again, we should now notice that unlike before where the force was only going up and down for the parts, we should have a force pushing the plane backwards. And let's press E to increase our thrust. and we can see the force is now pushing backwards. And we should still notice that the plane is very hard to control. So if I start to rotate left and right, I'm going to start losing control. And this is because our plane has not been very well designed. So let's now make some changes to our plane model. So the first thing I'm going to do is I'm going to duplicate this large center part. So I'm press Ctrl D, and I'm going to move this new duplicate part to the left. And inside of this duplicated part, we have two attachments. Now these attachments were used for the hinges, but we're not going to have hinges on this part, so I'm going to delete these two attachments. So we're just going to have a part that is welded to the seat. And then I'm going to go into View and enable Grid Material. And now I'm going to align this part over here. And I'm going to scale this part down to be around this big. And like so. I'm also going to make this part thinner, so it doesn't have much drag on the sides. I'm also going to scale these parts to make them thinner as well. Like so. I'm also going to make them slightly longer, so I have a bit more surface area on the top and bottom. And then I'm going to duplicate this new part we created and place it on the other side. Another problem that we had is when pressing the A and D keys trying to roll the plane, these two flaps never had much authority. And the reason for this is because these two flaps are very close to the center of mass, so they don't have much leverage on the roll. So it would be technically better to have these flaps at the ends of the wings, so they would have more leverage in rolling the plane. But for now, all I'm going to do is simply go into the part, select the hinge constraint, and I'm going to increase the steer float up to 40, so that when we try to rotate the plane, it's going to rotate these hinges 40 degrees, which is going to produce more drag in a direction to push stronger to rotate. And I'm also going to do the same for this part. So go inside, change the steer float to 40. Now, inside of our plane script, I have purposefully made a mistake in order to demonstrate a problem. So if we go into our plane script and go down to loop, we can see that we're using the assembly's linear velocity when calculating the velocity of the particles that are colliding with the part. Now, this is not technically 100% correct, and this is because this velocity is the velocity of the entire assembly of this model, but this wing on the side and this wing on this side may not have the exact same velocities. So let me now try to demonstrate this problem. When I start to fly, we will notice that the left and right wing will incorrectly have the same force applied to them, irrelevant of the rotation of the plane. So if I get on the plane and start flying, and if we take a look at the force on the left and right wing, and when I start to rotate left and right, you can see that they both stay the same because they're both using the assembly's velocity. If I start to spin, we can see that they still have the same velocity as one another. So to fix this problem, all we're going to do is go back into the plane script, and we're going to delete this line here, and we're going to replace it with data.part, and we're going to use the function getVelocityAtPosition, and then we're going to pass the part's position, which is the center of that part. And if we now test the plane again, we should notice that when we rotate the plane, the left and right wing now get affected independently. So let's rotate left and right, and we can see that the force on both the left and right wing are different from one another. And we will also notice that the plane now has angular drag. So if I rotate left and stop, the plane will automatically stop rotating. And if I rotate right and stop, the plane will automatically stop rotating. Okay, let's now talk about another problem that we have, and that is that some surfaces of a part are not out in the open. So for instance, this surface inside here should not affect the drag because it's being blocked by this part on the left. And for instance, if I made a duplicate of this part and moved it over here, now this surface inside on this surface over here should not be affected by drag. So we need to somehow disable some of the surfaces of each part. Now, in order to fix this problem, we have many options. One option would be to simply set an attribute on the parts telling the script how much a surface has been blocked. Another option would be to use the getPartBounds in box to detect any parts surrounding the surface of that part, and then would be to subtract the other part's surface area from your own surface area. For instance, let's say that this surface had a surface area of 1 and this surface had a surface area of 5. When we use the getPartBounds in box to detect this part, we would subtract this surface area, which is 1, from the 5, which would remain a surface area of 4 for this part over here. But this will get kind of complicated and I don't want to make this video too long. So what I'm going to do is I'm just going to simply shoot a ray out of the end of each part. So I'm going to shoot a ray out this side, out this side, out this side, and also from the top and bottom. And if the ray hits another part, I'm just going to disable the entire surface. Okay, so let's first create our raycast perims. And what we're going to do here is we're going to only allow the ray to collide with parts that are within this model. So that means if a player is standing right next to here, the ray won't detect another player or another object. It will only detect parts within its own model. So let's go back into our plain script. And at the top here, when we get the model, let's create our raycast perims. So I'm going to say raycast perims equals raycastperims.new. I'm going to set the filter type to include, and I'm going to set the model as the filter descendants instances. The next thing I want to do is calculate the offset from the part's position for the ray's origin. So what I'm going to do is say the part's position plus half of the size of the part, and then I'm going to subtract 0.1 so that we're not exactly at the edge and we slightly indent from the edge a small amount. Now, one thing we need to be careful of is if this part has a very thin size, for instance, let's say this had a size of 0.001, if we did 50% to the right and then we indented to the left by 0.1, now the ray is going to start outside of the part, and when we shoot the ray to the right, it's going to hit itself. So we're going to make sure to use math.max and set the value to 0 so that the ray offset cannot go into a negative value. Okay, so now below vector false, let's calculate our offsets. So to do this, I'm going to say local ray offset x, and I'm going to say 50% of size x, negative 0.1. And I'm going to use math max and make sure that the value does not go below 0. Okay, so the way we're going to block a surface from working is if we come down and look at our dot product, this dot product would be a value between -1 and +1. But if we clamp this value to not go over the value of 0, for instance, if we only allowed it to go from -1 down to 0, now the positive side of this axis will no longer have an effect on drag. So what I'm going to do now is inside of this parts table, we're going to shoot a ray and calculate the clamp value for each one of these 3 dot products. So to do this, what I'm going to do is I'm going to create a minimum x variable, a maximum x, a minimum y, a maximum y, minimum z, and maximum z. And what we're going to do here is we're going to say if, and we're going to shoot a ray from the position of the part plus we're going to add the right vector, and then we're going to use the ray offset, which we calculated up here. And this is going to be the ray's origin. Then we're going to shoot the ray towards the right side, and it's going to have a magnitude of 1. Then we're going to do the same, but this time we're going to have a negative here. So we're going to have the offset, but in the opposite direction. And then we're going to shoot the ray, but in the opposite direction. So we're going to have a -1 here. And if the ray cast is equal to 0, that means it failed to hit anything. We're going to allow the minimum to go all the way down to -1. But if the ray does hit something, we're going to clamp the minimum at 0. And then we're going to do the same for the max. So if this ray does not hit anything, we're going to allow the dot product to go all the way up to 1. But if this ray does hit something, we're going to clamp the maximum at 0. And we're going to do this for all the axes. Okay, so now that we've calculated the minimums and maximums of the dot products, let's now use that to clamp the dot product. So over here, I'm going to say math.clamp. And we're going to use the minimum and maximum to clamp this value. And we're going to do the same. So let's just copy this math clamp over to this one over here and this one over here. And we're going to use the minimum and maximum for Y on this one. And we're going to use the minimum and maximum of Z on the look vector. Now, because our ray cast detection system is not that advanced, we have a few problems. When this large part in the center shoots a ray out of the front, it's going to collide with this motor and disable the entire front surface. The same is true for the sides. When we shoot a ray out of the side, it's going to collide with this wing and disable the entire surface. So if we now fly the plane, we'll notice that the force for this large part only goes up and down and no longer goes back. So let's start flying. And we'll see the force only goes perfectly up and no longer has any backwards force. So in order to fix this problem, what I'm going to do is I'm going to get this motor and move it from the center so when we shoot the ray, it doesn't collide with the motor. And I'm going to duplicate this so we have a balanced force pushing the plane forward. And the same is true for the wings. So we can see that this is the line where the ray will shoot. So we need to make sure that this part is free so we don't block it. So I'm going to move this over here. And I'm also going to do the same on this side. And so that we have a little bit of lift on the back, because we now have the lift on the front of the plane, I'm going to duplicate this part and I'm going to create a small wing for the back over here, just to produce a little bit of lift. And let's make a duplicate of this and move it over here. And now the rays should no longer be affected by the parts. And if we now do another test flight, because this large part is no longer blocked by the motor, we should see that the large red line no longer goes perfectly up and down, but also has drag pushing the large part backwards. So let's start flying forward. And we'll see that this large part is now being pushed backwards and upwards at the same time. Now let's add wind to our flight physics. So if we look inside of Workspace, we'll see that there is a property called global wind, which by default is set to 000. Now we can incorporate this into our flight physics, and all we need to do is go into our plane script, and here where we calculate the velocity that the particles are colliding with the plane is simply add this global wind property to this velocity. So all we would need to do is say plus Workspace global wind. And now we can go into Workspace. We can select the 3 dots next to global wind, and we should see this GUI pop up. And here I'm going to set the wind speed to 100 studs per second. And then I'm going to go into yaw, and I'm going to rotate this until the wind is coming from the front and slightly to the right. And then I'm going to press the dots again to hide the GUI. And if I now do a test flight, we should be able to use the wind, because the wind is very strong, to hover in place. So what I'm going to do is I'm going to start flying forward. And once I get in the air, I'm going to reduce my thrust. And I'm going to use the wind, which is coming from this direction, to hover in place. And you can see that the wind still affects the drag of parts. Let's now add a tail wing to see how that affects the flight of our plane. So I'm going to duplicate this part over here, and I'm going to move this to the center, and I'm going to enable the mesh grid so I can see where the center is and make sure it's perfectly in center. And then I'm going to adjust the size. So what we should notice now is, because the wind is coming from the right side, it's going to come and hit the right surface of this tail, and this tail is going to have a force that pushes it towards the left, which is going to make the plane rotate towards the wind. So it's going to act a bit more like a dart flying through the air. So let's sit on the plane, and we can see that the plane starts rotating towards the wind. And now we're facing the same direction that the wind is hitting us in. And if we start to fly, we can see that the wind is pushing the tail to the left. And if we just leave the plane on its own, it should naturally try to go towards the wind. Let's now add dynamic air density. So currently the air density is fixed to a value of 0.01, and this means that the plane can keep going up and up and up, and because there's always going to be air density, the plane will never hit a limit in altitude. But in real life, as you get higher and higher, the atmosphere will get thinner and thinner, and it will prevent the plane from going too high. So let's go back into our plane script, and let's scroll down to the loop where we calculate the velocity of the air particles. And above this, I'm going to create a new variable called normalized air density. And this is simply going to be the value of 1 negative the height of the part. Now, depending on how quickly you want the air density to reduce, we can adjust this value here, and this value here will adjust how quickly the value of 1 will reduce down to 0. Another thing I want to make sure is, if we go below the height of 0, or if we go too high, that we clamp the value between 0 and 1. And for now, let's just simply print this value. So I'm going to say print normalized air density. So let's now test and see what it prints to the output. So we can see that it's currently printing 0.999, which is almost at maximum air density. And let's now start flying in the air. And we should see that as we get higher and higher, the air density gets lower and lower. So you can think of this as a percentage, so 1 being 100% and 0 being 0%. And let's now use the normalized air density to calculate the air density. So at the very top, I'm going to delete this variable over here. And over here, I'm going to create the air density using the normalized air density. And if we think about turbine engines, they also require the air to work. So I'm going to multiply the normalized air density with our thrust, and this is going to make that our engines no longer work once we have left the atmosphere. So I'm going to say thrust multiplied by normalized air density. And before we test the game, I'm going to remove the wind. So let's go over here and set the wind speed back down to 0. So let's now see what's going to happen if I try to fly out of the atmosphere. The first thing we should notice is as the air density decreases, so does my thrust and the drag of the parts. And once we get up to 0, I no longer have control over my plane, and my plane will start to fall back down into the atmosphere. And now that we've finished our dynamic air density, we can remove this print. Thank you for watching my video, and if you have any questions, feel free to leave a comment down below.